A camera the size of a small car just took a single photograph containing 10 million galaxies. And that one photo represents less than 1/20th of 1% of what this instrument is about to capture over the next 10 years. If a number like that gets your attention, stay with me, because what this new observatory just revealed is going to change how we see the entire night sky. And I want you here for every discovery that comes out of it. Hit subscribe now. Most people have seen images from the James Webb Space Telescope by now. Those incredibly detailed, close-up portraits of deep space circulating everywhere online. But something just happened on the ground, here on Earth, that deserves just as much attention. A brand new observatory in Chile has started producing images every bit as remarkable as anything Webb has captured, using a completely different approach. The facility is called the Vera C. Rubin Observatory, sitting at the summit of Cerro Pachón in Chile's Atacama region. In June 2025, it released its first official images to the public, taken with the largest digital camera ever built. Having followed this project for years, I can say without exaggeration that these are some of the most jaw-dropping astronomical images ever produced. Let's start with the hardware, because the numbers are genuinely hard to wrap your head around. The camera at the heart of this observatory is roughly the size of a compact car, weighing around 3,000 kilograms. It captures images at 3,200 megapixels, each single photo built from over 3 billion individual pixels. To put that in perspective, you'd need roughly 400 modern 4K televisions arranged together just to display one full-resolution image at its actual size. And it doesn't stop at one image. During a single night of operation, the observatory generates around 20 terabytes of data, moved from the mountain in Chile through a dedicated high-speed connection to a processing center in Miami, Florida, for distribution to researchers worldwide. Before we look at the images themselves, it's worth understanding who this observatory is named after. In the 1960s, at a time when women were rarely present in astronomy at all, Dr. Vera Rubin produced the first genuinely compelling evidence for the existence of dark matter, while also raising a family alongside her scientific career. It's fitting that a facility built to study the invisible structure of the universe carries the name of the astronomer whose work first proved that invisible structure was really there. Here's something that might surprise you if you're used to hearing about Hubble and Webb. Part of what makes space telescopes produce such clean images is simply their location, floating above Earth's atmosphere, avoiding weather and light pollution entirely. So why build something this ambitious on the ground? The answer comes down to location. Cerro Pachón sits in one of the driest, darkest, clearest patches of sky anywhere on Earth. That's why this stretch of desert already hosts several other major observatories nearby, including the Gemini South Observatory and the Giant Magellan Telescope. This region has proven itself repeatedly as one of the best places on the planet to point a telescope at the sky. This observatory isn't run by an agency like NASA. It's funded jointly by the U.S. National Science Foundation and the Department of Energy, managed by a research consortium. Inside, it sits the Simonyi Survey Telescope, the 7th largest in the world, with an 8.4-meter primary mirror paired with a 3.5-meter secondary. But the genuinely unusual part is a third mirror, 5 meters across. Most telescopes use a 2-mirror system. This one uses 3, giving it an unusually sharp field of view across a massive area of sky at once. Attached to that telescope sits the camera itself, officially named after the survey it supports, the Legacy Survey of Space and Time, or LSST. Built from 189 individual sensors, the Legacy Survey of Space and Time, or LSST. Built from 189 individual sensors and 3 enormous lenses of fused silica glass, each single exposure captures 10 square degrees of sky, an area equivalent to about 45 full moons side by side in one shot. Compare that to the Sloan Digital Sky Survey, which mapped about 35% of the sky over a full 20-year run. This new camera can cover the entire visible sky of the southern hemisphere in a single 3-day observing cycle, Roughly every 3 days, it accomplishes what took Sloan 2 full decades. The 10-year length of the survey isn't really about needing that long to cover more sky. It's about mapping the universe across time itself, building a searchable, ultra-high-resolution time-lapse of the entire night sky. This project has 4 specific scientific goals: investigating the nature of dark matter and dark energy, cataloging objects within our own solar system, monitoring transient events like supernovae and gamma-ray bursts, and mapping the structure of our own Milky Way in far greater detail than ever before. The first batch of images was released in June 2025, and after just over 10 hours of initial test observations, the observatory had already captured cosmic activity on an unprecedented scale. Millions of stars and galaxies, thousands of asteroids, all just a small preview of what's coming. One of the first images has been nicknamed the Cosmic Treasure Chest. Built from 185 individual exposures captured over 7 nights, it shows a section of the southern Virgo Cluster, roughly 55 million light-years away, the closest large cluster of galaxies to our own. This mosaic covers 25 square degrees of sky and contains an estimated 10 million galaxies. Look closely at the upper left section, and you'll find 2 large spiral galaxies dominating the frame, with a trio of galaxies actively merging just above them, thin threads of stellar material stretched between them. Remember, that 10 million galaxy count represents just 0.05% of the roughly 20 billion galaxies this observatory is expected to observe across its full 10-year survey. Another early release is an equally striking mosaic of 2 nebulae, built from 678 individual exposures gathered over about 7 hours. At its center sits the Lagoon Nebula, roughly 5,200 light-years from Earth, one of the very few star-forming nebula faintly visible to the naked eye from mid-northern latitudes. Compare this to an existing Hubble image of the same nebula from 2018, genuinely rich in detail, but covering only about 4 light-years across. This new observatory's mosaic, by contrast, shows a vastly wider view. Hubble's field of view in a single image covers roughly 1% of the Moon's visible surface area. This observatory's covers an area equivalent to 40 times the Moon's surface, roughly 4,000 times more sky area per image than Hubble. But this observatory isn't just producing beautiful pictures. In those same 10 hours of test observation, it identified 2,904 previously unknown asteroids, including 7 near-Earth asteroids, none of which pose any danger to us. For comparison, roughly 20,000 new asteroids get identified globally each year through every other observatory currently operating combined. This single observatory alone is expected to discover millions of new asteroids within just its first 2 years of full operation. It also detected 46 subtly pulsating RR Lyrae stars, a type of star commonly used to measure cosmic distances, with up to 100,000 more expected over the full survey. In its very first year of full operation, this observatory is expected to collect more optical astronomical data than every previous observatory in history combined. By the time the full 10-year survey wraps up, it's projected to generate around 500 petabytes of data, containing billions of cataloged objects and trillions of individual measurements. It's worth appreciating just how long this project has been in the making. Serious planning stretches back roughly 2.5 decades, with hundreds of scientists and engineers across multiple countries contributing to the telescope, the camera, and the computing infrastructure needed to process everything it captures. The camera itself was assembled at a national accelerator laboratory in the United States before being shipped to Chile and installed on the telescope in early 2025. The public unveiling happened on June 23, 2025, during a live event at the National Academy of Sciences in Washington, D.C., shared simultaneously with research institutions around the world. Dark matter and dark energy sit at the center of this project's mission because they're genuinely strange. Ordinary matter, stars, planets, everything visible, including us, accounts for only a small slice of everything that exists. The vast majority comes from dark matter, invisible and undetectable, except through its gravitational effects, layered on top of dark energy, an even stranger force believed responsible for the universe's accelerating expansion. Together, these make up roughly 95% of everything that exists. By repeatedly imaging billions of galaxies over 10 years and tracking subtle patterns in how their light bends, researchers hope this survey will reveal far more about how these invisible components actually behave. One of the more exciting technical capabilities is speed. Because the observatory scans such enormous sections of sky rapidly and repeatedly, its processing system detects changes between one image and the next almost immediately, issuing an alert to the global astronomical community within about a minute of the image being captured, meaning if something new shows up anywhere across the visible southern sky, researchers worldwide can point other telescopes at it almost instantly, rather than missing a fast-fading event entirely. Producing 20 terabytes of raw data every night for 10 straight years makes this one of the largest ongoing data engineering efforts in modern science. Machine learning systems play a major role in sorting through the flood of data, distinguishing genuinely new astronomical events from routine noise. And unlike some past major projects, this data is designed for much broader access. After certain proprietary periods, much of it becomes available to the wider research community, and eventually the public, meaning students and dedicated amateur astronomers may eventually work directly with observations from one of the most powerful telescopes ever built. What makes this project fundamentally different from past surveys is repetition. By returning to the same patches of sky roughly every 3 to 4 nights across a full decade, this observatory isn't building a static map. It's building something closer to a movie, capturing how stars flicker, how galaxies shift and interact, and how objects in our own solar system move over time. A star suddenly exploding as a supernova, an asteroid swinging unexpectedly close to Earth, a distant galaxy briefly flaring. These are inherently temporary events that a system built to watch the same regions again and again is specifically designed to catch. Based purely on what's already come out of just 10 hours of early test observations, thousands of new asteroids, tens of millions of newly cataloged galaxies, dozens of previously unknown pulsating stars, and 2 Mosaic images that instantly became some of the most detailed astronomical photographs ever released, it's genuinely difficult to overstate how much more is likely still to come once the full 10-year survey is running at complete operational capacity. If a project like this excites you the way it excites me, subscribe now, because we'll be covering every major discovery that comes out of this observatory as the data rolls in, and you won't want to miss what gets found next.